All right, so some other definitions we have to kind of get down. Systems and surroundings. I've already said a little bit about system. This is where things can get a little bit more tricky if you're not careful, especially when we're dealing with calorimetry problems, which is about what we're about to dive into. In essence, a system is what we're trying to measure, okay? So that could be as simple as a piece of metal changing temperature. It could be water where salt's dissolving, where both things are part of it. It could be a reaction. It could be just about anything we were looking at. So whatever we are measuring, and again, that can get a little convoluted at times, so I'll work with you and we'll kind of get that figured out. And then the surroundings is everything else. So a lot of times we do our experiments in what's called a coffee cup calorimeter. And for the most part, everything within that coffee cup calorimeter is the system, and everything outside of that coffee cup calorimeter, so the classroom, the school, the universe, is the surroundings. And again, what we're measuring a lot of times is the system. So this can be a little confusing if you are in physics. Older physics terminology would always look at the surrounding, and everything would be measured based off the surrounding. So when you jump into chemistry and all of a sudden we're looking at the system versus the surroundings, that can be a little confusing. So just kind of keep that in mind, that if you're taking both classes, you may have to kind of switch gears going back and forth between them. Two terms we've already talked about, exothermic and endothermic. So exothermic is where energy is released, and again, this is both kinetic and potential, but what we're actually measuring is the kinetic energy change. So again, heat is looking at kinetic energy, or is the measurement of kinetic energy change, but it is due to both potential and kinetic energy changing. Keep in mind that this is delta H, okay, and delta H is a product here. So we're having our reactants and our products, and energy is being released, so it is also a product. Okay, endothermic, of course, is heat is being used, therefore delta H is a reactant. So all of our reactants, delta H is over here, it's required for the reaction to go, and then of course we have our products forming. So what do we need to know about this? Exothermic energy is being released, heat is being released, kinetic energy is being released. Well, what is kinetic energy? It is measured by temperature. So if kinetic energy is increasing or being released, temperature is also increasing. So exothermic is typically designated by it feeling hot to us. Okay, so this is any of the reactions we've done where it's gotten warm or it's released energy visibly. So think about the magnesium strip that we put into the Bunsen burner and it let off the really, really bright light. That is an exothermic reaction. It feels hot to us. A fire burning is hot to us, exothermic. Endothermic energy is being taken in, meaning we're actually losing kinetic energy, or kinetic energy of the system is decreasing. Therefore, temperature is going to decrease. So what we're going to feel here is cold. The reaction's getting cold of some sort. And keep in mind, this is not when we are physically putting heat or taking heat away. So this is not just putting ice in a freezer or putting fire to something. This is when the reaction itself is releasing energy and therefore feeling hot, or taking in energy and therefore feeling cold. Okay, so these are some of the things we need to know. Now, what we're going to dive into first is the first law of thermodynamics and enthalpy, and then we'll go into entropy and Gibbs free energy as we progress through this material. So the first law of thermodynamics is one you're already fairly familiar with. It's basically energy cannot be created or destroyed, or the conservation of energy. And it's basically saying the universe has constant energy. Energy cannot be created or destroyed. That leads into enthalpy, which is dealing with that energy, both kinetic and potential, and how it moves and flows within a system. Okay, and again, this can be due to work or heat being produced. So we are not dealing with work because we don't have pressure changes. We're dealing with temperature changes or heat changes. Okay, so we typically will call enthalpy either delta H, or we'll call it heat of reaction, and heat, of course, is where the delta H comes from. And if you're looking through your book or reading your book through this chapter, you'll see this weird equation where Q and P and work and all this other stuff are involved. It's simplified in the fact that Q equals delta H, and again, that's simplified because we are assuming pressure is staying constant and no work is being done. This is why in the last unit we could take Q from step 1 and add it to the delta H of step 2, and we were calling delta HQ, because they're essentially equal to each other because no work's being done, pressure is remaining constant. Okay? So from there, we're going to talk about something we're already familiar with as well, which is calorimetry. Q equals mc delta T, our NCAT, where N is, of course, still mass. Okay, C is our specific heat capacity, and delta T is our change in temperature. Okay, and of course, hopefully we know that this weird little triangle thing is delta, and that is change. So we'll see a lot of deltas through this chapter. We'll see delta H, delta S, delta G, and of course delta T. That means change. So specific heat capacity, we saw in the last chapter, it is basically the amount of energy required to raise 1 gram of a substance by 1 degree Celsius or Kelvin, either way. Remember, it has the units of joules over grams degrees Celsius, which you see down here as well. Okay. 2 different specific heat capacities that we can talk about are generic specific heat capacity, which is per gram, but we also have molar heat capacity, which you don't see as much. But obviously with mole, it is a chemistry term. A lot of times in AP chemistry, we deal with specific heat capacity, but I do want you to know that molar heat capacity exists as well. Okay? All right, so let's kind of look at one of these problems and see what we're going through. We used this equation last chapter, so I'm not really worried about the math behind it, but it's the problem solving of the math that we need to work through and make sure we're comfortable with. Okay, so first and foremost, a 75-gram sample of aluminum at 100 degrees Celsius is added to 300 milliliters of water at room temperature, also known as 25 degrees Celsius. I think we talked about that back in acid bases. 25 degrees Celsius is room temperature and is a constant value. So anytime you see room temperature, you can assume this 25 degrees Celsius. Okay? The temperature of the water is changed to 39.2 degrees Celsius, or the final temperature of water is 39.2. What is the specific heat capacity of the aluminum? So what we need to recognize here is we have our coffee cup calorimeter. Okay, and forgive the very poor drawing. Let's try that again. Okay, and we'll be playing with coffee cup calorimeters here shortly. It has water in it. Okay, and that water is initially, so Ti, at 25 degrees Celsius. Okay, we're then going to take a piece of aluminum that has an initial temperature of 100 degrees Celsius, and we're going to drop it into this water. Okay, and of course this is in a styrofoam cup, so it's insulated, so we assume no heat is transferred outside of the cup. It's only transferred to the water. Well, what happens if I take something hot and put it in something cooler? Well, energy is transferred. So we have this piece of aluminum down here, and we're told that the water's final temperature is 39.2 degrees Celsius. Okay, so what does that mean? That means the final temperature for the piece of aluminum is also going to be 39.2 degrees Celsius. This is that whole idea, if I take a hot cup of coffee and leave it on the countertop, what's going to happen? It's going to end up being the same temperature as the room around it. Why? Because heat is transferred from hot to cold, and the reason it's doing that is the gas molecules, or the molecules themselves, are colliding with each other, and as they collide, energy is transferred from high energy to low energy. So, in other words, the molecules where it's warmer and they're moving faster are going to transfer more energy, or when they collide to the molecules that are moving slower or colder. And eventually what's going to happen is the amount of energy transfer is going to equalize, and therefore the temperature is also going to equalize or be the same. So in this case, the piece of aluminum starts at a higher temperature and is going to decrease to 39.2 degrees Celsius. Water starts at 25 degrees Celsius and increases into 39.2 degrees Celsius. Okay, so we are looking for the specific heat capacity of aluminum. So Q of aluminum equals mc delta T. Okay, and the C is also of aluminum. So we have the energy of aluminum is going to be equal to the mass of aluminum times the specific heat capacity times the change in temperature. So we don't know Q of aluminum yet. We know the mass of aluminum is 75.0 grams. We're given that. we're asked to find the specific heat capacity of aluminum, and we're told the change in temperature is 100 to 39.2. So 100, and actually it's 39.2 minus 100 because it's always final minus initial. So technically our change in temperature here is a negative 60.8 degrees Celsius. So we still have two variables, so something's wrong here. We're not quite yet ready to solve for the specific capacity of aluminum. Well, what's missing? What's missing is the fact that the energy transferred from the aluminum is going to be equal to the energy absorbed by water. Why? Because energy cannot be created or destroyed. So the Q of aluminum is going to equal the Q of H2O. And in technicality, one's going to be positive and one's going to be negative. And in this case, aluminum's going to be negative because it's losing energy, and water's going to be positive. Okay, because again, energy cannot be created or destroyed. It's being transferred from aluminum, negative, it's losing, to water, positive, gaining. Okay, so what we're left with is this idea of the Q of H2O is equal to the mass of H2O, and we don't need to put that there, times specific heat capacity, and change in temperature. Okay, so Q of H2O is going to be equal to the mass of water. Well, where do we get that? We get that from this guy right here, because we know the density of water is equal to 1 gram per 1 milliliter. So we have 300 grams of water. Easy peasy. Specific capacity is not on here, but if you'll remember from last chapter, is 4.18 joules per gram degrees Celsius, and our change in temperature is 25 to 39.2. In this case, 39.2 minus 25. So keep in mind, when we're calculating change in temperature or changing anything, it's always final minus initial. Okay, so our change in temperature here in this particular situation is 14.2 degrees Celsius. So now we just solve it out. So we have 300 times 14.2 times 4.18. And that's going to give us a Q for water equal to 17,806, and with, let's say, 3 sig figs because of our temperature change, because technically this is going to be 4 sig figs because it's 300.0. I just didn't put it down here correctly, but we'll do 3 sig figs. So 17,800 joules. Okay, and of course that again is positive as we've already discussed. So now we go back up here to our Q of aluminum, and we make it negative, because again, aluminum is losing that amount of energy because they are equal to each other, and we now solve it out. Okay, so we have our 17,800 divided by 75 and negative 60.8, and we're given a specific heat capacity of aluminum is 3.91 joules per gram degree Celsius. Now, I'm not 100% positive if that's its actual specific heat capacity or if this is a problem I made up, so don't go to the index and see if it matches, because it may not, but the math should be there, okay? And this is actually one of the labs we're going to do when I come back, is the specific heat capacity of a metal lab, where you're going to be determining the identity of a metal based off of this type of data. Okay, that's all I've got time for to work with you through right now. What I want you to do is, let me see if I can find one that you can actually do right now. What I want you to do is work through these multiple choice problems, or at least this first multiple choice problem. Let's start here, because this is very similar to what we just did, so it's pretty straightforward, and we'll come back and look at that answer in just a moment. Thanks.